All right, today we're going to talk about exponential functions and their graphs. So all equations we have considered up to this point are algebraic equations. Now we're going to look at exponential functions, logarithmic functions, and these are called together transcendental functions. All right, the definition of an exponential function. The exponential function of f with a base a is denoted by f of x equals a to the x power, where a is greater than 0, a is not equal to 1, and x is any real number. So the reason we don't make a equal to 1, because then you just have a function that's just a all the time, okay? Any x can be any real number bigger than 1, though. Well, it can be any real number bigger than 0, as long as it's not 1. Okay. So some things here: evaluate an exponential function allows you to solve problems like this. F of x is 2 to the x, and let x equal negative 3.1. So this would be a problem you'd want to do on your calculator. So you get out your handy-dandy TI-84 plus C Silver Edition graphing calculator, and you'd push 2, and then your power key is right above the division sign, and then you'd push negative 3.1. Make sure you're using the negative key down here on the bottom of your calculator and not the minus sign over here, because the minus sign is going to give you an error. So we plug that in, and this becomes 2 to the negative 3.1 power is approximately 0.1166. All right, 2 to the negative x power, where x is pi, this becomes 2 to the negative pi power. So I'm going to go 2 to the negative, and then I'm going to use my pi key, which is the same key as my power key. I just got to push the second key first. And that's going to be approximately 0.1133. 0.6 to the 3/2 power. So 0.6, push my power key. Now, with the newer TI 84s, if you just push 3 divided by 2 up here, it'll all stay in the power. You need to pay attention, though, because some of the older calculators, if you just type it in as 0.6 to the 3 divided by 2, what it'll do is it'll do 0.6 to the 3rd power, and then it'll take your answer and divide it by 2, and that's not what you want. Okay? So be really careful of that. So you would have to put it in parentheses if that's the case. I don't have to on this one. So 0.6 to the 3/2 is approximately 0.4648. And then 1.05 to the 2x power, where x is 12. So that would be 1.05 to the 24th power. And that's going to come out to be about 3.225. Now you should do all these on your calculator and compare the answers to what I got and make sure that you're getting the same thing. Okay, graph the equation y equals 2 to the x power. So 2 to the 0 power is 1, because anything to the 0 power is 1. 2 to the 1st power would be 2. 2 to the 2nd power would be 4. 2 to the 3rd power would be 8. Okay, so you can see this thing is growing up. Now, 2 to the negative 1 power, that's 1/2. 2 to the negative 2 would be 1/4. This thing is going to approach 0, but it's never going to get there. So this graph is going to look like this. This is called exponential growth right here. Okay, 2 to the x power. To the negative x power. Well, that's basically going to flip these things around, because your negatives are now going to be positive. So 2 to the negative x, where x is negative 3, is going to be 2 to the 3rd power. That's going to be 8. And then 2 to the negative negative 2 power is going to be 4. 2 to the negative negative 1 power is going to be 2. 2 to the 0 power is still going to be 1. And we're going to go this way here. It's never going to reach 0, but it's going to get as close as you want. So this is going to go like this. This would be an exponential decay problem. Okay, properties you need to know. A to the x times a to the y is a to the x plus y. So I don't like to just throw these up here and say, hey, you got to know these. I like to show you that they work. So I'm going to give you some examples here. So let's say we had a was 2. Well, let's just use a. So x would be 2 and y would be 3. So a to the second times a to the third. If I break this down to what this actually means, a to the second means a times a. And a to the third means a times a times a. And that together is a to the fifth power, which just happens to be a to the 2 plus 3 power. So you can see that you're going to add the exponents there. Okay, with this one, a to the x divided by a to the y is a to the x minus y. So let's say I had a to the fifth over a to the third. So what this means is a times a times a times a times a divided by a times a times a. Now, I can cancel things, and I'm left with a squared, which would be a to the 5 minus 3 power. So I just subtract the exponents. A to the negative x is 1 over a to the x. So anytime I have a negative exponent, that means if it's in the numerator, it's going to flip it down to the denominator. And if it's in the denominator, it's going to flip it up to the numerator. So kind of the way you can look at this is if you follow the pattern, okay, I've got a to the fourth, okay, a to the third, this is a times a times a times a, this is a times a times a squared is just a times a to the first is a to the 0 is 1. So if you follow the pattern, what's it doing? Well, a to the fourth, each time I would be dividing by a. Okay, so a to the fourth divided by a is a to the third divided by a is a squared divided by a is a divided by a is 1. So if I continue that pattern, a to the negative 1 would be 1 divided by a. And then a to the negative 2 would be 1 divided by a, which is going to be 1 over a squared. And so it just flips that thing over. A to the 0 is 1. We showed that with the pattern here. A times b to the x power is just a to the x times b to the x. So it would be like this. A times b to the third power would be a times b times a times b times a times b, which if I just reorder this is a times a times a times b times b times b, which is a to the third, b to the third. Okay, a to the x to the y power is a to the x times y power, so I would multiply exponents here. So if I look at this, it would be like a squared to the fourth would be a squared times a squared times a squared times a squared, which is a times 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 a, which is a to the eighth, which is a to the 2 times 4 power. Similar here, a over b to the x power. Let's say we had a over b to the third power. Okay, that's going to be a over b times a over b times a over b. So when I multiply fractions, I multiply the numerators, that's a times a times a. And I multiply the denominators, that's b times b times b. Well, that's just a to the third over b to the third. So it fits the pattern here. The absolute value of a squared is equal to the absolute value of a squared, which is just a squared. Okay, so this one, if you kind of just look at some numbers in here, put some positive or negative numbers in there, it's going to work. So obviously if it's positive, this is always going to work because like 3 squared is 9, absolute value is positive is 9, okay, and this would be 3 squared again, which would also be 9, and 3 squared. The time you want to look at this one is negative, okay? So let's say I had absolute value of negative 3 squared. Well, that would be absolute value of 9, which would just be 9. And over here, that would be absolute value of 3 squared, but the absolute value of 3 is just positive 3 squared, which would be 9. And then this would be 3 squared, which would be 9. So they're all the same. Oops, I'm sorry. This should be negative 3 squared like that would be 9. Okay, so there's your properties. Parent functions, so here's your 2 to the x power. Here's your 2 to the negative x power. You know, if I put 3 in here, it's pretty much the same graph, except that it's a little steeper. So over here, if it was 3 to the first power, 3 to the first power would be here. 3 to the 0 power would be still 1. 3 to the second power would be 9. So that'd be here. 3 to the negative 1 power would be 1/3. It's going to actually be below the line here. But this thing's going to be, it's going to look like this. It's going to be under, it's going to cross, and it's going to be larger. Okay, and the same thing over here, except it's going to be above the line here. It's going to cross right there, and then it's going to be below the line there. Okay, the natural base e. So there's a number called e. E is an irrational number. It's approximately 2.7182818 or 128. It's often called the natural base, and it's written with a function like this: f of x equals e to the x. So if you look on your graphing calculator, right here next to the 4, there's a key that says ln that stands for natural log, and right above that in the blue is e to the x. That's your exponential equation, or your exponential function. So basically, it's just this number to the x power. So it looks pretty much like this, except it's 2.718. Okay? So it looks very much like those other things. Now, this is a number that is useful because it occurs in nature all the time. So the number e can be approximated using this formula right here, although we're rarely going to use that for large values of x. Okay, use a calculator to evaluate the function f of x equals e to the x when x equals one of these numbers. So here's what I'm going to do. I'm going to push second and then the natural log key, so that gives me e, and then it gives me an exponent. I'm just going to put -2 in there and hit enter. And this should come out to be 0.135335 and some change. Okay, so you can pause the video right here and try these and make sure that you get these numbers written down, and then you can look at what I'm going to do next. So go ahead and pause the video, do these next 3 problems, and then jump back on here and look at what we get. Okay, so e to the 0.25 power, so I'm going to push second natural log, so that gives me the exponential function, put in 0.25, that's going to be approximately 1.284. This one here, e to the negative 0.4 power. So e to the negative 0.4 is approximately 0.6703. And then e to the 2/3 power. So e, whoops, wrong key. E to the 2 divided by 3. Now, if you got an older calculator, you want to put the 2/3 into parentheses. So you should get 1.9477. Okay, so very simple to do. All right, here's two formulas that you will want to know because you will be tested, I promise, on both of these. So this is compound interest formula, A equals P times 1 plus R over N to the NT power. This is your continuously compounded interest formula, A equals PE to the RT power. So let's look at what these mean. P stands for principal. So principal is the amount of money that you either borrow or you put it into the bank. That's how much you deposit. That's your principal. R stands for interest rate. Interest rate. Okay, T stands for time, and it's always in years. So if you're doing something for months, you got to convert it to years as a fraction of a year. Now, what's this N thing? It's in two places. This stands for the number of times the money is compounded per year. And the thing is the more times you compound it per year, the more money you end up getting. Okay, or paying if this is like a loan that you've taken out. Now, over here, an A stands for the amount. Sometimes this is a B and it stands for balance. This is how much money you'll have in your account. Okay, so over here, same thing, amount. All right, P is principal again. R is again interest rate. And again, T is time in years. And E is just the number E. That's all it is. It's not a variable. It's a number. Okay. So you need to know these two formulas. I would write them down every single time that you do a compound interest problem. You need to write that formula down. You need to have those memorized, okay? Because you use these a lot. All right, so a total of $9,000 is invested in an annual interest rate of 2.5% compounded annually. Find the balance in the account after 5 years. So this is compound interest formula. I'm going to write the formula down first. Okay, so A equals P times 1 plus R over N to the NT power. Another reason that I write down the formula is not just to memorize them, but it tells me where all the numbers go. Okay, so here I've got 9,000. That's my principal. It goes right here. So that's going to be 9,000. Okay, my interest rate, 2.5%. That's going to go right here. That's 0.025. I have to move the decimal 2 places to the left here. Okay, 1%, 0.01. I cannot tell you how many times I tell somebody, oh, it's 1%, and they put down 0.1. That's 10%. You're going to have way too much interest if that's the case. Okay, 5 years. That's my time. That goes up here. And then n, where's n? Well, n comes from this right here. Annually. Annually means once a year. So there's going to be a 1 there and a 1 there. And then this is going to equal the amount. So now I get out my calculator. Now when I type this into my calculator, I can type it in all at once if I want. You just got to be careful how you do it. So you would type it like this. You would type 9,000 times, open parentheses, 1 plus, open another parenthesis, 0.025 divided by 1, close this parenthesis, close the second parenthesis, to the 1 times 5 power. Again, with a newer calculator, you don't have to put those parentheses around it because it will just keep you up in the power until you jump down out of it. So, if you type it just like that, it should tell you the answer. So, 9,000 times, open parentheses, 1 plus, open another parenthesis, 0.025 divided by 1, close the first parenthesis, close the second parenthesis, to the 1 times 5 power, and that comes out to $10,182.67. That's the amount of money that you have in the account now. And that's what it asks you for. Okay, now you got to be careful because sometimes it will ask you how much interest did you get, and if that's the case, you need to take the amount and subtract the principal, and that will tell you how much interest. So there's $1,182.67 in interest in this problem. Trying to keep everything color coordinated here for you so that if you're looking at the notes, you can find everything easy. Okay, a total of $12,000 is invested at an annual interest rate of 3%. Find the balance after 4 years when the interest is compounded A, on a quarterly basis, and B, continuously, and compare them. Okay, so I said earlier, the more times you compound the interest in a year, the more money you get. And that's because you're getting a little bit of interest on the other interest instead of just waiting till the end of the year to get your interest. Okay, compounded continuously is like being compounded every instant. Okay, that's as much as you can get. So let's look at both of these. We'll write down the formula here. A equals P times 1 plus R over N to the NT power. There's my compound interest. And then over here, this is my continuously compounded interest formula. So the principal is $12,000 on both of these, so the principal is going to be $12,000 on both. Okay, so I've got 1 plus, okay, and here I've got E. All right, so my rate R is 3%, that's 0.03, and here my rate is 0.03. And let's see. How many times it compounded? So it's compounded quarterly. So compounded quarterly tells me that it's going to be 4 times a year. So N is going to be 4. And then T is time, and that's going to be compounded for 4 years. I need a different color. Let's try this. So T is going to be 4. Oops, and I forgot to make that. Okay, so there you go. And this equals A. All right, so let's figure out what these are. I've got everything filled in. So the first one is 12,000 times open parentheses 1 plus open second parenthesis 0.03 divided by 4, close the first parenthesis, close the second parenthesis, exponential power 4 times 4. All right, this comes out to be, whoops, Amy says that I'm going to have $13,523.91. Okay, over here, I'm going to go 12,000 times second natural log key, so that gives me my E key. It already puts me up in the exponent. I just go 0.03 times 4. And I get $13,529.96. So I got an extra, what, $6.05 in interest by compounding it instantaneously rather than quarterly. Okay. If I were to compound it, monthly, that'd be n would be 12. It would be a little bit more than this, but it'd still be less than this. If I were to compound it annually, this would be 1 and 1, and this would be even less than this. So there you go. Okay, radioactive decay. Let Y represent a mass in grams of radioactive strontium, which is this right here, whose half-life is about 29 years. The quantity of strontium present after T years is 10 to the 1/2, or 10 times 1/2 to the T divided by 29 power. Okay, so what is the initial mass when T equals 0? Okay, so now, in case you don't know, anything that's radioactive has a half-life. That half-life varies depending on what the item is. So with strontium, it's 29 years. If you have plutonium, it's much longer than that. Okay? And basically what happens is you have, let's say you had a pound of strontium, then 29 years later, you would have a ½ pound of strontium, and you would have a ½ pound of something else. It would decay to something else. Okay? After another 29 years, you would now have a ½ pound of strontium 90, and then you would have 3/4 of a pound of something else, and it just keeps going down by half each time. So this is just an exponential equation here. What is the initial mass when T is 0? So I could plug 0 into this thing, and I would get 10 to the 1/2, or times 1/2 to the 0 divided by 29 power. Well, that's just 0. And 1/2 to the 0 power is 1. So this is 10 times 1, which is 10. So you'd have, 10 grams? Is that what we had here? Whatever my unit of measure is. Yeah, it's in grams. So this would be grams. I started with 10 grams. So in 29 years, I'll have 5 grams. In 58 years, I'll have 2.5 grams. Now, it doesn't disappear. The other stuff becomes some other object, okay, some other element. So, after 58 years, I'll have 2.5 grams of strontium, and I'll have 7.5 grams of whatever strontium decays to. How much of the initial mass is present after 80 years? Okay, so, it's easy to do half-life if you're doing it on the, whatever the half-life is. But what about 80? 80 is not divisible by 29. So all I do is I plug it into the formula. So I'd go 10 times 1/2 to the 80 divided by 29 power. So I get out my calculator, 10 times 0.5 to the 80 divided by 29, and I get approximately 1.4765 grams. So it's almost 3 half-lives. Not quite. Okay, population growth. So the approximate number of fruit flies in an experimental population after t hours is given by Q of t equals 20 times e to the 0.03 t power, where t is greater than or equal to 0. Find the initial number of fruit flies in the population. Well, you can kind of look at this thing. This is going to end up being the initial number. Okay, because if I put 0 in here, e to the 0 is just 1, and 1 times 20 is 20. So you can do that part in your head. Okay, 20 fruit flies. So I'm given 20 fruit flies to do my experiment. Now, how large is the population after 72 hours? Okay, so I just plugged 72 in for t. So 20 times e to the 0.03 times 72 power. All right, 20 times second e 0.03 times 72. Bam! I got 173.4, but that's going to be, we'll just round it to the nearest because you can't have a partial fly. And we'll put approximately. And if you've ever had fruit flies in your kitchen, you learn pretty quick that those things practically appear out of nowhere, and they multiply very, very fast. Okay, you can graph this on your graphing calculator. So if I was going to do that, I just go y equals. Make sure if there's any equations in there that you clear them out first. And then I'd put in the first equation, 20 times e to the 0.03 x power, and hit enter. And then check your window and hit graph. And nothing showed up in my graph. Now what does that mean? Well, that means that my window is not in the right place. So my graph went from negative 10 on the bottom to positive 10 on the top, and negative 10 on the left to positive 10 on the right. Okay, so I really don't need negative time, so I can get rid of the negative x's. So I'll go to my window and just start at 0. Max of 10 hours is fine. Now my y min, I definitely don't need negative flies. In fact, I start with 20 flies. So, and it went up really fast. So let's go from 0 to, on the max, let's go to 5. Let's go to 5,000. And we'll make the y scale 1,000 just to see. Actually, make it 500. Okay, and then hit graph again. And nothing happened again. All right, what's my problem here? Y equals, I put the equation in there right. Oh, 72 hours too. Okay, so let's make my window, let's make my x go from 0 to 100. Let's count by tens. Okay, so my scale here, my x is going to go from 0 to 100 by tens. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then it's going to go from 0 to 5,000 by 500s. So let's try graphing it again. Oh, and now I can finally see a line, and it's down here. So it's very flat. I mean, it runs right along here. So that means that this is too big. So let's go back to our window again, and let's adjust my y max to 500 instead of 5,000, and we'll make the scale 100. See what happens then. Okay, so now I got a better looking graph. So sometimes the hardest part is just figuring out what it is that you want to graph. So here's 100, 2, 3, 4, 500. And now this graph looks kind of like this. Okay? Should be a nice, it should be smoother than that. Not a very good graph. Looks more like that. Okay, and if you wanted to know, okay, how many flies did I have after 100 hours, I could go second table, and okay, for some reason mine started me out at 224 hours. I got 16,576 fruit flies. But if I could go table set and set it to 100 hours, and then go back to my table, 401. Okay. And again, that'll give you approximately, it's not going to give you the exact number. All right, so what do we got here? We've got a little lesson for you. It's got some exponential growth shown by Timmy, who's 6.5, and a couple other ways to look at exponential growth. These are the problems I want you to do. Here is the pages that I want you to do out of the book, or the problems, and I've gone ahead and put better pictures of these in Google Classroom so they're much clearer. So take a look at those, and I will talk with you later.